is going to be the central nervous system. Your mental and physical activity and homeostasis are controlled by your nervous system. I mentioned last week that it's broken down into two divisions. That's the central nervous system, which includes your brain and spinal cord, and the peripheral nervous system. So I'm going to talk about the central nervous system today. So within your the network of cells that communicate with the body and the body with the brain, it's divided into a very organized manner so that each part operates efficiently. So the two major divisions, the central nervous system and peripheral nervous system. The central nervous system, or the CNS, as I said before, is the brain and the spinal cord. So we've got, let me fix my iPad. Here we go. So the way it's going to be broken down is you've got your nervous system, you've got the central nervous system and the peripheral nervous system. The peripheral nervous system is going to be broken down into two other divisions. That's the motor and sensory. And then the motor division is broken down. Is it the motor one or the sensory? I can't remember. We'll get there later anyway. Either the motor or the sensory division will be broken down into two more. Okay, so the spinal cord carries messages from the body up to the brain, and then the responses are sent from the brain through the spinal cord and down to the body.
Did you know that the most important part of your entire body is your central nervous system? Your central nervous system, also known as the master system, is made up of your brain and your spinal cord, and it controls every single function in your entire body. In fact, your central nervous system is so important that it's the only body part that is totally encased in bone for its protection. Starting at the top is your brain. And your brain is the central processing unit of your body, and it coordinates and computes all the electrical signals that are sent throughout your nervous system and your entire body. So from your brain, electrical impulses or signals are sent down your spinal cord and travel all the way to the base of your spine. And branching off of your spinal cord are these fine thread-like structures called spinal nerves, and they exit between the vertebrae of the spinal column to supply all your muscles, cells, and organs, and from there, the electrical impulses are sent back up to the brain in a feedback loop. And at every level in your spine, the exiting spinal nerves supply specific muscles and organs. For instance, starting from your lower back, these spinal nerves supply such structures as your legs, reproductive organs, bladder, kidneys, and colon. As we move up the spine to the upper back or thoracic spine, the exiting spinal nerves supply such organs as your liver, stomach, heart, and lungs. Moving up further to your neck, these nerves supply such structures as your eyes, ears, throat, and arms. Now, in a healthy spine, your spinal bones or vertebrae are in proper alignment, and the cushioning or shock absorbers between the vertebrae, called intervertebral discs, are thick and healthy. As such, correct spinal movement is possible, and the spinal nerves are able to freely exit the spine, sending nerve impulses from the brain to the targeted muscles and organs without any interference. However, from poor posture, falls, a car accident, or some other injury, your vertebrae can become misaligned. This misalignment is what chiropractors call vertebral subluxation complex, or just subluxation. When a subluxation occurs, your vertebrae can then press on these existing spinal nerves and interfere and block these nerve impulses. When this happens, nerve damage begins and your body starts to dysfunction. Although potentially painless at first, symptoms can develop rapidly. And when a subluxation is left untreated, your spine begins to decay. Your discs begin to thin and wear down, and your vertebrae start to deform and degenerate, leading to the development of these spurs or osteophytes, which then further compresses and damages your nerves. So when a subluxation occurs in your lower back, it can cause back pain, sciatica, bladder weakness, irritable bowel syndrome, and erectile dysfunction. A subluxation in your upper back can cause respiratory problems, digestive problems, and decreased energy levels. And subluxations in your neck can cause headaches, dizziness, tinnitus, carpal tunnel syndrome, numbness, tingling, and weakness to one or both of your arms. Fortunately, chiropractic can help. In fact,
okay, so he's going to go on about chiropractic now, which is fine. But the important part to understand here is when they were talking about the spinal nerves that exit the spinal cord, it's pretty proportional. I'm trying to find pretty proportional to where in the body it is. So the spinal nerves that exit the spinal cord near your neck are going to control the organs and the body structures that are up here. When you go down the vertebral column, the spinal nerves that come out here are going to control organs in your thoracic cavity. And then, of course, if you move down the body, then again, it becomes proportional. So if you're down at the lower end of the body down here, then that's proportional to your digestive system down here, your reproductive organs, and your legs. So one of the things that he mentioned, and there was something called sciatica. Oops, sciatica. That's an SCIA. And that is basically when you have one of the nerves down at your lower back, it gets pinched and you feel pain all the way down your legs because of the location of the spinal nerve. So that's why posture is really important. So it's important to remember to keep your back straight and not hunch over, even when you're young, because if you, posture requires the contraction of back muscles, and it's just like working out. Like if you don't practice it, then the muscles become weak and you just kind of end up having this kind of hunched over posture. And then that means that your vertebral discs, which are these cartilage, little pancakes of cartilage in between your vertebrae, they can get compressed and end up having some nerve damage. So that's your central nervous system. The peripheral nervous system is everything that's not included in the brain and spinal cord. Now, in the peripheral nervous system, we identify neurons based on which direction they're carrying the message. You remember from last week, I said that action potentials, which are the nerve impulses, they move in only one direction. So you need to have two sets of networks, basically. You've got one network that carries messages towards the CNS and another set that carries messages away from the CNS. So afferent neurons carry messages from the body to the brain and spinal cord, and efferent neurons carry messages away from the central nervous system to the body. And that's part of the peripheral nervous system again. All right, the main focus for today is going to be on the structure of the brain. The brain is divided into many different parts. And so we're going to go through that and look at just how organized it is. Obviously, the brain is responsible for overseeing the day-to-day operations of your body. Not only does it control all of your conscious activities, like the fact that you're actively listening right now, you're actively looking at a screen, you might be using your skeletal muscles to highlight in your book or to make notes or whatever, but it also at the same time is responsible for all of your subconscious activities, like your breathing, your heart rate, if you ate breakfast already, your digestion, even blinking. So the biggest thing that I want you to remember as we go through all of these is that your brain is constantly working, right? Besides the heart, it's pretty much the only part of your body that works 24/7 from like the minute that the organs are formed until the day you die. In fact, true death doesn't really occur until there's no more electrical activity of the brain. So you can say that the brain is the last thing to die. So you could have complete and total organ failure so that there's a machine that has to breathe for you and there's a machine that has to pump your heart for you, but you still have electrical activity in the brain. True death is what we call brain death. Oh my gosh, move that little menu thingy. There we go. Now, the brain weighs about 1.5 kilos, which is 2% of your total body weight, and it contains about 100 billion neurons. The main parts of your brain are the cerebrum, which is this big part here. Okay, for humans, that's the largest part of our brain. That's where you can say a lot of the quote higher level thinking, speech, memory, problem solving, that kind of stuff. You've got the diencephalon and the lower brainstem. These basically connect your brain to the spinal cord. They're kind of like inside in here. This is the lower brainstem. The diencephalon is up here. It's the upper brainstem. And then finally, you have the cerebellum, which is this part in the back lower part. Okay, so together these are the brainstem. The diencephalon is the upper brainstem, and the lower brainstem for some reason wasn't special enough to get its own separate name, just called lower brainstem. And each of these are going to be broken down into more specific areas. And the important thing to remember is that the labor division in the brain is very specific. So you have very specific areas of the brain that are responsible for interpreting different types of sensory information that comes in. For example, hearing is interpreted. Hearing is interpreted in the parietal lobe. Vision is interpreted back here in the occipital lobe. As you see the optic radiation. But we'll go through all of that. Okay, so here you see in the darker red color, that is the cerebrum. Here you can see the diencephalon, that's the upper brainstem. This is the lower brainstem, cerebellum. The cerebrum is the largest portion of the brain. I want to draw your attention to the fact that it is highly folded, and there is only one reason in biology why things are highly folded, and that is surface area. Okay, cerebrum, highly folded outer layer. Now, if you look at the brain from the top down, you will see that there is a clear division in what we call the cerebral hemispheres. You have a right and a left hemisphere. Now, the interesting thing is that, there's a generalization that people are generally either right or left brain dominant, and that a lot of the kind of like artsy, musical, creative activities occur on the right side of the brain, and then the more analytical, mathy, sciencey type logical things occur on the left side of the brain. I don't think it's that simple. I think there's different things that are interpreted on both sides, but in general, they say if you're right dominant, then you're more creative, and if you're left dominant, you're more analytical.
Nothing that they did worked.
So did you see how she just kind of all of a sudden like jerked to the left side, her left side? I'll rewind that a little bit. You can see she kind of just all of a sudden just kind of moves to the left. That's because that's a seizure.
Worked.
Right there.
She was constantly falling to the left. And it got so bad that one of us had to be on her left side all the time.
It was to the point where I was having seizures every 3 minutes, and that wasn't cool.
Now, there is a specific reason why she's always falling to the left side, and that is because the right hemisphere of the cerebrum controls the left side of your body, and the left hemisphere controls the right side of your body. So she is having problems with her right hemisphere. Now, encephalitis, anything that's cepha or cephal is referring to the brain. And I don't know if you remember what I told you way back when, what the suffix itis means, inflammation. So encephalitis is a general term for inflammation of the brain.
The doctor explained that the only way they could treat it was to take out the half of the brain that was affected.
So you might be thinking, are they nuts? Like they're going to literally remove half of her brain. Like, what are they thinking? Well, the thinking is that when you are very, very young, like I think she was 3 or 4 years old when this started happening, when you're very young, your brain is in what's called a very a state of plasticity, which means it's very moldable, like it's still forming. We talked about synapses earlier, like the synaptic cleft, right, is the gap between neurons. When you form a new synapse, like every time you learn something new, you are connecting two new neurons together that weren't connected before. I often make the analogy that it's quite like going into the jungle and then like you want to create a superhighway, right? So when you go into the jungle, it's full of trees and undergrowth, and it's really difficult even just to walk through. This is like when you're ignorant of a fact, like you don't know something, right? When you start to learn something new, that's kind of like when you start clearing the brush away and the undergrowth and you start like cutting down the trees. The more that you practice this thing, the more that you are the more that you read about it, the more that you practice it, you clear the pathway for your highway more and more and more until finally you have a completely clear path, and then you can start to put down your cement, and then your cars can drive on it, whatever. That's a really good analogy for learning something new. So if, for example, you are listening to me now, but you're like kind of half asleep or whatever, that's like if you are kind of sort of trying to clear the jungle out, but like not really. But if you come back and you watch the video again later, or if you read in your book or you practice the vocab, like the more that you go and you practice it, the more solid you're making that connection between those neurons. And that's called a synapse, right? When you make a connection. And it's so powerful, this idea of like practicing things, that they have done studies where you have gymnasts, like even Olympic medal gymnasts, if they don't have the opportunity to go to the gym to practice their routine, they will sit and meditate and picture themselves in their head going through their routine, and it actually makes them better. That's how powerful it is. Like we always use the term or the phrase mind over matter, but it's literally true. We can actually use our brains to help us solidify either gymnastics routines, or like if you play an instrument and you picture yourself in like the way that your fingers move on a guitar string or on a piano or something like that, it helps, because it's not the same as physically doing it, but it's like the next best thing. So the scientists are going to literally remove half of her brain in the hopes that her left hemisphere will kind of take over, because she's so young. She's, like I said, 3 or 4 years old when this happened. She's so young that it is possible for her brain to adapt. If you did this to an adult, it would not work.
I am a very positive person. A lot of times I'll joke that they took out the mean side of my brain and they only left the happy side.
If you had asked me 25 years ago if it was possible to take out half the brain and still have functioning life, I would have said, you've got to be crazy. But here we are.
Life now with half a brain is, for me, is no different than anybody else. I've been married 4 years. I live on my own with my husband. I'm really glad my parents did what they did, because I wouldn't be where I am now if I had had the surgery any later or had waited any longer.
Okay, so here is an actual human brain that is cut in half. You can see here is the diencephalon, that's the upper brainstem. This is the lower brainstem, and here's the cerebellum. The only thing connecting the right and left hemispheres is this structure right here that looks like a sideways J. That is called the corpus callosum. It is a heavy band of the axons of neurons. And again, it's the only thing that connects the right and left hemispheres of the brain.
Does being creative mean you're right-brained? Or if you like math and science, are you definitely left-brained? More importantly, did a quiz on Facebook give you this idea? For over a century, we've known certain parts of our brain are specialized for certain tasks, noticing that people with injury or damage to specific parts of the brain often lack the ability to do very specific things, like speak, or identify objects, or even recognize the faces of loved ones. Because evolution doesn't care about making sense, the left side of your brain controls the right side of your body. Anything presented in your right field of view is only seen by the left side of your brain, and vice versa. But in your standard brain, that one-sided information can't be hidden from the other, because the two hemispheres are connected by a neuron superhighway called the corpus callosum. When these fibers are plugged in, the brain's two hemispheres work together in seamless harmony, and we don't even notice that different functions of daily life reside in different parts of the brain. But if these cords get cut, it's a different story. In the 1940s, brain surgeons came up with a new way to treat epilepsy, splitting people's brains. A seizure is like an electrical storm that puts the brain in overdrive, so build an impenetrable barrier to contain the storm, stop the seizures. And this actually worked. People with so-called split brains were mostly the same, but doctors started noticing some weird side effects, like when choosing clothes to wear or picking out food, each side of their body was operating independently from the other. Scientists could finally look at what actually happens if the two halves of a brain are separated. And it completely changed our notions of how the brain is organized. When a word is shown to the right side of a split brain, the patient can't say what they saw out loud, but they can draw it with their left hand. Kind of creepy. Normally, motor signals get confused when you try to draw two separate pictures at the same time with each hand, but a split brain patient can do this task as if they're operating each hand completely separately.
So it's important to notice that they've colored the words in a specific way, because if your left eye sees the word elephant, that means that your right hand is going to draw it, because remember, the left side of the brain controls the right side of the body. And again, the right eye is going to have the left hand draw the lion.
Separately. These spooky experiments showed many brain functions are lateralized. They're generally divided into the left or right side. The ability to speak, for example, takes place in a spot called Broca's area that in most people is on the left side of the brain. Decades of these experiments show that generally the right side of the brain processes spatial and temporal information, the when and the where, and the left side controls speech and language. But that doesn't mean in different people one half dominates the other. More like our brain is arranged in compartments, a collection of fuzzy little modules all working together to form what we know as us. But why use tiny bits of our brain to do complex tasks instead of the whole thing? Basically because our brains are big. We have more neurons than most animals, which means more connections. In fact, we have too many neurons for them all to link up. If each neuron in our brains was connected to every other, our brains would be 12 miles in diameter, and information wouldn't be able to travel fast enough across our neuron networks. Now, smaller circuits mean more efficient heads. Thousands of ants can work together as a coordinated colony without each individual getting instructions from the queen. Our brain combines those functional modules in a similar way, only instead of building anthills, they come together to somehow build that thing we call consciousness. How a unified mind can emerge from a brain made of tiny packages with different responsibilities is one of the greatest questions in not just neuroscience, but all science. And we still don't have a complete answer. But splitting brains in two has taught us that breaking our 3 pounds of think meat into smaller and smaller pieces probably won't solve the puzzle. Consciousness isn't one specific thing we can put our finger on. We could study a symphony by describing the physics of individual sound waves, but it loses a little bit of its beauty along the way. And looking at the function of single neurons in a brain likely won't let us decode how we think and perceive the world. Now, we should understand how the individual instruments are played, but also remember that your brain is more like an orchestra, different sections working together to produce beautiful music. Stay curious.
So that's a really perfect analogy in looking at how the brain works. It's like a symphony. So different parts of the brain have specific functions. I want to go back to what he said, if I can find it. There it was here, Broca's area. So Broca's area is the part that allows you to speak. So if there's a problem in Broca's area, like sometimes somebody will have a stroke on the left side of their brain in Broca's area. And what happens is if they have a stroke that happens in this area of the brain, they might be able to recognize the object, but they can't say it, right? And I got a video later on about aphasia, when people don't realize that they're actually speaking gibberish. They're like saying words that don't match. So like if you hold up a pen to them, they'll call it like an elephant or something, because they've got a problem in the Broca's area. So going back to the splitting the brain thing. So if you look at a lot of the experiments that were done, even as recent as like 50 years ago, they were like completely barbaric in how we treated it. So they used to do, for people that were mentally ill or had seizures, they used to do something called a frontal lobotomy, which is where they took a metal spike, like literally a metal spike, a giant metal nail. They would put it in the corner of your eye, and then they would take, of course, you're not awake when this happens. They would take a hammer and they would ram the nail up into the frontal lobe. And of course, yes, you're not crazy anymore, but you are like catatonic, which means you're just sitting there like a vegetable, because that's where scientists believe your personality is. Anyway, so if you have a problem with the left side of your brain, then that's going to lead to some speech problems. And depending on the kind of damage to the brain, it leads to different types of speech problems, whether you recognize an object but can't physically say what it is, or you are saying, you think you're saying what it is, but it's actually not. Anyway, we'll get into all that. So we're going to look at the cerebrum first. And there are, you can see based on this diagram, there are deep grooves in the cerebrum that are going to separate the cerebrum into 4 lobes. You've got the frontal lobe, you've got the parietal, okay, up here. You have the temporal, and finally you have the occipital lobe. The very outer layer of the cerebrum is called the cerebral cortex. Remember what I told you about the word cortex, just like before we had the renal cortex. This is outer portion. That's what cortex mean. And cerebral, of course, refers to the cerebrum. Now, the cerebral cortex is only about 2 to 4 millimeters thick. And scientists estimate that it contains about 10% of your brain's total neurons. These folds or convolutions are going to make room for a large surface area. Of course, remember I told you folds, surface area, they go together. The cerebral cortex is important for sensory processing and motor responses. Separate areas control auditory, visual, body sensation, and motor processing. So here's a nice diagram to kind of break down in general where a lot of sensory information is interpreted. So like I said, in the frontal lobe, that's where they identify that personality is located. Also your emotions, a lot of your motor functions. Motor just means movement. Your problem solving and reasoning is here in the frontal lobe. Now, the frontal lobe for humans is much larger than any other species, which is why we have a great ability for problem solving and reasoning. That doesn't mean that no other organism can solve problems or can reason, because we've got our cousins, which are the great apes like chimpanzees, gorillas, orangutans. They are also able to problem solve, and even as far down in the evolutionary chain as the octopus can actually solve problems. The parietal lobe is responsible for sensory information, so like touch and pain receptor, heat, things like that. Your temporal lobe, you've got speech, that's where Broca's area is, language and hearing, and vision is interpreted in your occipital lobe at the back. Okay, and I'll get into the other parts when we talk about cerebellum and brainstem.
Language is an essential part of our lives that we often take for granted. With it, we can communicate our thoughts and feelings, lose ourselves in novels, send text messages, and greet friends. It's hard to imagine being unable to turn thoughts into words. But if the delicate web of language networks in your brain became disrupted by stroke, illness, or trauma, you could find yourself truly at a loss for words. This disorder, called aphasia, can impair all aspects of communication. People who have aphasia remain as intelligent as ever. They know what they want to say, but can't always get their words to come out correctly. They may unintentionally use substitutions called paraphasias, switching related words like saying dog for cat, or words that sound similar, such as house for horse. Sometimes their words may even be unrecognizable. There are several types of aphasia, grouped into two categories: fluent or receptive aphasia, and non-fluent or expressive aphasia. People with fluent aphasia may have normal vocal inflection, but use words that lack meaning. They have difficulty comprehending the speech of others and are frequently unable to recognize their own speech errors. People with non-fluent aphasia, on the other hand, may have good comprehension, but will experience long hesitations between words and make grammatical errors. We all have that tip-of-the-tongue feeling from time to time when we can't think of a word. But having aphasia can make it hard to name simple everyday objects. Even reading and writing can be difficult and frustrating.
So I'm sure, like she just said, we've all had that moment where we have like that, we're trying to think of the word, and we're like, what is that? We try to describe what it is. Aphasia is like having that, but like all the time.
So how does this language loss happen? The human brain has two hemispheres. In most people, the left hemisphere governs language. We know this because in 1861, the physician Paul Broca studied a patient who lost the ability to use all but a single word, tan. During a postmortem study of that patient's brain, Broca discovered a large lesion in the left hemisphere, now known as Broca's area. Scientists today believe that Broca's area is responsible in part for naming objects and coordinating the muscles involved in speech. Behind Broca's area is Wernicke's area, near the auditory cortex. That's where the brain attaches meaning to speech sounds. Damage to Wernicke's area impairs the brain's ability to comprehend language.
So this is interesting because Broca's area is how, like, the area where we produce sounds. And so a lot of that has to do with, what do you call that? Like muscle training. So if you learn a new language and there's new sounds that you have to make with your mouth, a lot of times I've always found like the best language teachers or pronunciation teachers are the ones that address like where your tongue is in relative position to like your teeth. Like my French teacher, when I was in high school, always said when you pronounce the L, that you want to put your tongue flat against the roof of your mouth to get that correct sound out. So that's all Broca's area. Wernicke's area is even more interesting because that is where you assign meaning to words. So this is like when you're growing up and you're, like a baby and your mom's like, mama, dada, whatever. This is assigning significance to the sounds that you're hearing. Because if you think about it, language is just a bunch of sounds that we have assigned a meaning to, like different kinds of meanings. So if you go to a new country like Sweden, you hear them like, none of those sounds mean anything. But if you were to actually study it and understand like geflurgen is like means this, you're using your Wernicke's area. Very, very interesting.
Aphasia is caused by injury to one or both of these specialized language areas. Fortunately, there are other areas of the brain which support these language centers and can assist with communication. Even brain areas that control movement are connected to language. fMRI studies found that when we hear action words like run or dance, parts of the brain responsible for movement light up, as if the body was actually running or dancing. Our other hemisphere contributes to language too, enhancing the rhythm and intonation of our speech. These non-language areas sometimes assist people with aphasia when communication is difficult. So how common is aphasia? Approximately 1 million people in the US alone have it, with an estimated 80,000 new cases per year. About 1/3 of stroke survivors suffer from aphasia, making it more prevalent than Parkinson's disease or multiple sclerosis, yet less widely known. There is one rare form of aphasia called primary progressive aphasia, or PPA, which is not caused by stroke or brain injury, but is actually a form of dementia in which language loss is the first symptom. The goal in treating PPA is to maintain language function for as long as possible, before other symptoms of dementia eventually occur. However, when aphasia is acquired from a stroke or brain trauma, language improvement may be achieved through speech therapy. Our brain's ability to repair itself, known as brain plasticity, permits areas surrounding a brain lesion to take over some functions during the recovery process. Scientists have been conducting experiments using new forms of technology, which they believe may encourage brain plasticity in people with aphasia. Meanwhile, many people with aphasia remain isolated, afraid that others won't understand them or give them extra time to speak. By offering them the time and flexibility to communicate in whatever way they can, you can help open the door to language again, moving beyond the limitations of aphasia.
Okay, so I think this is the video where you're gonna see an interview with a man who is suffering from aphasia. So some of the things that he's saying make sense and other things don't, and you'll hear him kind of use certain words inappropriately, like over and over again. I mean, I don't mean that they're inappropriate words, but they're words that don't match what he's trying to say. So in this fluent aphasia, basically he thinks that he makes all the sense in the world, and his speech pattern, meaning like the way that it sounds like he's speaking, sounds normal, but the words don't make sense.
Hi, Byron. How are you?
I'm happy. Are you pretty? You look good.
What are you doing today?
We stayed with the water over here at the moment and talked with the people for them over there. They're diving for them at the moment. They'll save in the moment. He'll have water very soon for him. With luck for him.
So we're on a cruise and we're about to
We
get to
will
Juneau.
store it right here and they'll save their hands right there for them.
And what were we just doing with the iPad?
Right at the moment, they don't show a darn thing.
With the iPad that we were doing. Like here?
I'd like my change for me and change hands for me. It would happen. I would talk with Donna sometimes. We're out with them. Other people are working with them. I'm very happy with them.
Good.
This girl was very good and happy. And I play golf and hit other trees. We play out with the hands. We save a lot of hands on hold for us, other hands. I don't know what you get, but I talk with a lot of hand for him. Sometime. Am I talk of any more to saying?
All right. Thank you very much.
Thank you very much. I appreciate it, and I hope the world lasts for you.
Thank you. It's been a pleasure. Bye-bye.
Have a good day.
Yeah, so you can see sometimes it makes perfect sense, like have a good day. You heard him talk like I was able to play golf, but then other thing like I had hands and hands for him and on the water, meaning that they were on a cruise ship, but that's aphasia. Okay, now below the wrinkled surface of the cerebral cortex is what's called white matter, and these are the axons of the cortical neurons. Cortical meaning coming from the cortex. Oops. So cortex is a noun, cortical is an adjective. The white matter links specific regions of the cortex with each other and also with other neural centers, of course, because our brain is constantly getting a huge amount of information, and some of that is related, some of that not. So it has to be able to distinguish between the kinds of information that it's getting and relay that to the proper part of the brain. Okay, so here you can see that looks like an MRI or a CAT scan. I'm not really sure. But either way, it's using, yeah, some kind of scan. It looks like an MRI, which stands for magnetic resonance imaging. And so you can see the white matter here, and then this is the cerebral cortex. We call this gray matter. Next, we have the upper brainstem, which is also called the diencephalon. So this is a great diagram of what it looks like. Looks kind of like a weird alien creature when it's by itself. But you can see its position within the brain. It kind of starts right in the middle of the cerebrum. Now, the whole brainstem, the upper and lower brainstem, you can see divided into two parts. This is the whole thing. So the upper brainstem in this diagram are only the purple parts. That includes the thalamus and the hypothalamus. The lower brainstem includes three more parts, which are the midbrain, the pons, and the medulla oblongata. Like, I love that name, medulla oblongata. Okay. So, and then you can see in yellow down here, those are the spinal nerves that start to come off of the spinal cord. But the brainstem is there to connect the brain to the spinal cord. Okay. Upper brainstem, diencephalon. Now, the diencephalon, which you can see just, this is the corpus callosum here, and this is the upper brainstem here. It contains important relay centers for information entering and exiting the brain. The upper relay center is called the thalamus. This directs incoming sensory signals to the proper area of the cerebral cortex. Because it's basically the last structure, and you can see based on the diagram here, thalamus, and then we follow the line to here. That's the thalamus right there, right underneath the corpus callosum. Now, this is the last structure. If you think about the way that sensory information goes up through the spinal cord, it comes up this way. This is the last structure before you hit like the brain proper. So the thalamus is what decides what kind of information is coming in and then which lobe basically it has to go to. Now the hypothalamus is just below the thalamus, and that is linked to several other parts of the brain. The hypothalamus is a connection between the nervous system and the endocrine system. It directly and indirectly controls hormone production. So again, here is the entire brain stem, including the corpus callosum. This is your corpus callosum here. You have your thalamus, which is here, the hypothalamus, which is here, and this is your pituitary gland. The pituitary gland is basically the boss of the endocrine system, and the pituitary is controlled by the hypothalamus, and that's why you can see the hypothalamus directly above the pituitary. The rest of this is the cerebellum, and the rest of this is the lower brainstem. Okay, so the diencephalon is just the thalamus and the hypothalamus. The thalamus, super important relay center for putting the incoming action potentials, directing it to the proper lobe of the cerebral cortex. And the hypothalamus is the connection between the nervous system and the endocrine system. Now, parts of the diencephalon and cerebrum are included in a system called the limbic system. You can see it here in green. So you can see the thalamus and the thalamus, hypothalamus, and the hippocampus, amygdala. These are all part of the limbic system. This is in the temporal lobe and deep within the cerebral cortex. The limbic system plays an important role in emotion, memory, and motivation. And then finally, we get to the lower brainstem. We're seeing narrower, using the narrowing of the brainstem because we're leading into the spinal cord here. But basically, if you, the way that I identify the lower brainstem is by this right here, the structure of the pons. It's like, it looks like a little like sticky outy thingy. And I know the pons, you just remember pons is the middle part of the lower brainstem. So you have the midbrain, pons, and medulla oblongata going in order. So midbrain, pons, medulla oblongata. I will get to the reticular formation in a minute, which is part of that as well. Now, the midbrain, which you can see here in green. So here we have the thalamus. The hypothalamus will be underneath there. Midbrain here. This is an important relay center for visual and auditory information. If you think about it, it makes sense because auditory information, if you can see, it's here because we're coming out from here. So this purple area or pink, whatever, corresponds to this pink area. Then you've got green, green, blue, blue, and then kind of an orangey, whatever, which is here. So this is the midbrain. This is smack dab in the middle of where hearing is located, and then behind it is vision. So this is where hearing comes here, vision goes to the back, and that's the midbrain's job, is to separate those two. The pons, which is here, and you can see that here. This is a relay center between the cerebrum and the cerebellum, which makes sense because it's right in front of the cerebellum. So it kind of relays between the cerebrum and cerebellum. The cerebellum is mostly responsible for homeostatic activities and muscle coordination. So like your heart rate, your breathing rate, all of the subconscious things you don't have to think about. And then your muscle coordination is back here. And of course, the things that are going on in your cerebrum have to relate to coordinating with your body on how to move. For example, if you are walking in the street and all of a sudden you hear a car horn like, that's going to be translated here. And then you're going to have your problem solving and reasoning skills here, basically relaying information to your cerebellum to have your muscles move so that you can run out of the way. And finally, medulla oblongata. This contains nerves that also serve as a relay center. So if you want to dumb it down and make it as easy as possible, the whole lower brainstem is also a relay center. Now, in order to try to figure out what they're relaying, just think about their position, right? It's all about position. Oh, shoot, I'm 5 minutes over. Crap. Somebody should have stopped me. Why didn't you stop me? Oh, no. What the heck?